Hey guys, this is section 5.5. It's rational functions and their graphs. So when we say rational function, we mean a function in the form f of x equals p of x over q of x. So it's a fraction, right? P of x and q of x are polynomial functions, and q of x cannot be zero. Why? Because if you divide anything by zero, you get, right? 0 divided by 10, that's okay. 10 divided by 0. You are not allowed to divide by 0. It won't work. It's an error. Just like how we say that a slope where the bottom number is a 0 is, we say there is no slope or it's undefined, right? Okay, so when you have a rational function, we are going to learn how to identify the domain, identify vertical asymptotes. Vertical means up and down, right? Vertical. A vertical asymptote is a line that the graph never crosses. So in this case, number one right here has two vertical asymptotes. This is a vertical, it's really hard to see because the graph is tiny and the lines get really, 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 really close to the asymptote. But this is a line that this will never cross. This function will never cross this line. This function will never cross this line. Okay, that's a vertical asymptote. Horizontal just means this way, right? So a horizontal asymptote, same thing. The graph will never touch that line, I should say. Um, and then we also have oblique asymptotes or slanted asymptotes, okay? Then we want to be able to graph a rational function. So here's a rational function. Could you graph it if you had to? All right, that's what we're doing today. So the first question says, use the graph of the rational function to shown to complete the statement. Sorry. So here it is. Here's the graph, and it says, as x approaches -2, that means from the negative side, right? So I said that that was an asymptote at -2. So as we approach, asymptotes are supposed to be dashed. As we approach -2 from the negative side, right, of x equals -2, as we approach it, what is f of x, or what is y doing? So our y, right, is this line. So as we approach -2 from the negative side, y is going towards -infinity. As x approaches -2, but from the other direction, what is this function doing? According to y, it's going up now, right? So we're going to say it's approaching infinity. As x approaches infinity, here's my x-axis, as x approaches infinity, what does f of x approach? It looks like, it's hard to see, but it looks like it's approaching 0. And as x approaches -infinity, again, it looks like y is approaching 0. Good. Okay, next we're going to find the domain of the rational function. We're going to use set builder notation to write the domain. One second. Set builder notation is just a different way to write it. Set builder notation looks like this. X such that, you could say all real numbers, or you could say x cannot be 0, for example. That would be a type of set builder notation. All right. So to find the domain of a rational function, what we want to do is we want to set the denominator equal to 0, solve that for x, and then the domain will be every value except what x equals in the denominator. Why? Because again, just like we were doing 10 divided by 0, we don't want this to ever become 0, right? If this is 0, then that is something that we cannot graph. So our domain is going to be all real numbers for x except anything that would make our denominator 0. So what we want to do is we're just going to look at that denominator. In this case, it's x squared minus 25. And we're going to set that equal to 0 and solve for x. Okay? There is more than one way you can do it. You can either just set it to 0, set it equal to 0, just like that. So add 25 to both sides, and we get x squared equals 25. Now I need to take the square root of both sides to just find x, right? So the square root of x squared is going to be equal to positive or negative square root of 25. So that means x is equal to positive, the square root of 25 is 5, or negative 5. So that's one way to do it. Or if you like factoring, you can also say, take that denominator and factor it. X squared minus 25 becomes x plus 5 times x minus 5, right? We set that equal to 0, so now we're going to set that equal to 0, and then each of those gets set equal to 0. X plus 5 is 0, x is negative 5, x minus 5 equals 0, add 5 to both sides, we get x equals 5. Again, the domain is not x equals negative 5 and x equals 5. The domain is x equals everything except those 2 points, okay? So the way we're going to write it in set builder notation is open a bracket, x such that x is not equal to negative 5, x is not equal to 5. I start with a smaller number and then follow with the bigger number. All right, number 3, you're done. That is the domain. X is all real numbers except negative 5 and 5. Next one is f of x equals x plus 8 divided by x squared minus 4x. Again, we're just taking the denominator, x squared minus 4x, setting it equal to 0. Here I'm going to factor, okay? I'm going to factor because I see that both of those terms I can take an x out of. So I'll take the x out, and I'm left with x minus 4 equals 0. Good. Take each of those terms, set them equal to 0. X equals 0. X minus 4 equals 0. Here, x is just equal to 0. Here, we add 4 to both sides, and x equals positive 4. So we're going to write it as x such that x is all real numbers except it cannot be 0, and it cannot be positive 4. Good. That's the domain of the rational function. Last one, number 4. We're just taking the denominator, x squared plus 64 equal to 0. If you look at that, you're thinking, okay, 64 is a perfect square, x squared is a perfect square. Can I just say it's x plus 8 times x minus 8? You could if it was a minus, right? The difference of 2 squares. But we're adding it, so we cannot use that. That will not be true. We can't really factor it. We can use the square root method, right? So x squared plus 64 equals 0. Subtract 64 from both sides, we get x squared equals negative 64. Take the square root of both of those. Square root of x squared becomes plus or minus square root of negative 64. That means we have x equals a negative or a positive. What's the square root of negative 64? It's 8i, right? 8i is not a rational number. It's an imaginary number, so that is not going to show up on our graph. So we can just say all real numbers, because there is no real number I can put in here, square it, add it to 64, and it will give me 0. Okay? If I were to graph this in Desmos, which I guess I could, hold on. All right, I graphed it. It's not a great one, but it looks like this. And what you can see is there is not really a point where you can see a gap in the domain, right? When we looked at number 1 here, there was a gap in the domain. It never hit x equals, what would we say? -2, right? And it never hit x equals +2. Here, I'll graph number 2 for you. All right, if you graph number 2, it's red. So not the black one, the red one. And we found for number 2 that x can be any real number except -5, which is right here, and +5, which is right here. So you see the gaps in the domain when you graph it. Whereas here we said that that the domain is all real numbers, and that is because there is no point at which the graph is not an x value. You can just say from -infinity to +infinity. Okay? That's what the domain is for today. For number 5, they're just giving us a picture, a tiny, tiny picture of the graph, and they're asking us what the domain and range of the function would be. Okay? So domain, remember, is all x values. We're going to start with -10, right? It looks like it's going infinitely in that direction because the graph just ends. So we're going to say it's from -infinity, and then it stops because there's an asymptote. Okay, it stops at -2. It does not include -2, right? Union with, it starts again at -2, but doesn't include it, and goes forever in a positive direction. So that would be the domain of this picture, the graph picture, I should say. And then the range is just, we're going to do the same thing, but on the y-axis. So on the y, we're going to start at the bottom. That arrow's going that way, so I'm going to say it's from -infinity to wherever it stops, right? This dotted line is the asymptote, and so that's what it's going to approach and never touch. So we're going to say -infinity to -3, union with, from -3, it's going to go up forever. -3 to infinity. Notice that they're not brackets, they're parentheses because it never touches -3 and it never touches -2. Good. All right, so let's talk about a vertical asymptote. A vertical asymptote is this dashed line, a vertical line in which the function value goes to infinity on the y-axis. So this is going towards infinity, right? Positive infinity. Down here is going towards -infinity. So a vertical line in which function values goes to plus or minus infinity as the x value approaches the line, but it will never touch the line, okay? In rational functions, vertical asymptotes occur where there are no common factors between px and qx, okay? If there are common factors, there is a hole in the graph instead. If the domain of the rational function is just real numbers, there is no vertical asymptote, right? And then in number 4, we didn't see a vertical asymptote either. There's no number I could square plus 64 to get to 0. A graph never crosses a vertical asymptote, and vertical asymptotes are drawn as dashed lines, but are not really part of the graph, okay? To find a vertical asymptote, there might not be any, but to find a vertical asymptote, you want to first factor the function. Factor the numerator and factor the denominator so that you can simplify it. So if this was x plus 1 on top divided by x times x minus 1 parentheses x plus 1, you could then factor out the anything common. So if x plus 1 was common to both, you could factor them out. It's not, but that was just an example, okay? You're going to factor the numerator, factor the denominator, simplify it, get rid of anything that's common if you can, and then set the denominator to 0, just like we did to find the domain, okay? So here we have x times x minus 1, and we're going to set it equal to 0. X times x minus 1, set it equal to 0. take each of those factors, set them equal to 0, x equals 0, and x minus 1 equals 0. That just stays as x equals 0. This is x equals 1. So there are vertical asymptotes at x equals 0 and x equals 1. Let me graph this for you. All right, I'm going to share my screen to show you Desmos. Here is x plus 1 divided by x times x minus 1. This is what the graph looks like. I zoomed out just to show you that there are 3 parts to it. And we said that there are vertical asymptotes at x equals 0 and x equals 1. I'm going to go ahead and zoom in now. You can see x equals 0. So from the left side at x equals 0, we're approaching infinity on the y-axis. On the right side of x equals 0, we're approaching negative infinity on the y-axis. And then the other vertical asymptote was at x equals 1, right here. And we'll see that on the left side of x equals 1, we're approaching negative infinity, and on the right side of x equals 1, we're approaching positive infinity. So that's what the vertical asymptotes are. We found them because those are places where if I put in that value, my denominator will be 0, and that is not graphable. Okay? Same thing for 8. F of x equals x minus 9 divided by x squared minus 10x plus 24. So again, your first step is to factor both the numerator and the denominator. The numerator is already in factored form, but the denominator, x squared minus 10x plus 24, we might be able to factor that, right? What do we need? We would need, if we go all the way back to our factoring days, we would need two numbers that multiply to equal 24 and add to equal negative 10. Multiply to equal C, add to equal B. I would say negative 6 and negative 4, right? Negative 6 minus 4 is negative 10. Negative 6 times negative 4 is positive 24. So x squared minus 10x plus 24 factors to x minus 6 times x minus 4. Leave the top the same, x minus 9. If there was a binomial that was common to both the top and the bottom, you would then cancel it, right? But there is not. Now, we just set that denominator equal to 0. X minus 6 times x minus 4 equals 0. X minus 6 equals 0 becomes x equals 6. X minus 4 equals 0 becomes x equals 4. So we have vertical asymptotes at x equals 4 and x equals 6. If you were to graph this in Desmos, you would see that the graph does not ever cross 4 and does not ever cross 6, and that on the y-axis, at both 4 and 6, it will be approaching infinity and negative infinity on the y-axis. Good? All right, number 9 is f of x equals x divided by x squared plus 7. Make sure we factor it. I don't know that we can. X just remains x. X squared plus 7. I don't see any common factors to it. We could try... No, that would just be solving for x. There's no way to factor x squared plus 7 because there's nothing in common between x squared and 7, right? Now, it's asking us to solve for... Set the denominator equal to 0 and solve for x. X squared plus 7 equals 0. I can't factor it, but I can use the square root method, right? So that would be x squared equals negative 7. Come in, take the square root of both sides. The square root of x squared is equal to plus or minus square root of negative 7. So that means x equals plus or minus square root of negative 7. You can't really factor. You can't really simplify the square root of negative 7, so it just remains as plus or minus square root of negative 7. That's not a real number, so there is no vertical asymptote for number 9. Show you the graph of that. All right, so the green line is x divided by x squared plus 7. This was our old one. We saw our asymptotes at 0 and at 1. Turn that one off. Here, there are no asymptotes because the square root of -7 is not a real number, so there's not a point on the graph where we will have a vertical asymptote. Let's go on to number 10. We have h of x equals x plus 2 divided by x squared minus 4. Let's factor that. X plus 2 just remains x plus 2. X squared minus 4 becomes x plus 2 times x negative minus 2, right? That's the factored form. Now we finally see an example where we can cancel out common factors. Those were common to the top and the bottom. So now we just have, it's not 0 on the top, it's 1 over x minus 2, right? We're going to set that equal to 0. X is 2, so we have one vertical asymptote at x equals 2. Show you the graph. All right, this is x plus 2 divided by x squared minus 4. We can see an asymptote at x equals 2. We also had x plus 2, right, before we factored it out because it was common to the top and the bottom. So if I go over here on my line to -2, I see that it's a hole. It's hard to see because we can't zoom in close enough, but if you know where it is and you run your mouse across it, that hole will become open because -2 is undefined, okay? It's undefined just like the asymptote is undefined, but it's just a hole because there were common factors between the numerator and the denominator. That's what that meant right here. If there are common factors, x plus 2, x plus 2, there is a hole in the graph instead of a vertical asymptote. Good. All right, number 11. We're going to now talk about horizontal asymptotes. Remember when we looked at the graph, vertical meant up and down. So this is a vertical asymptote. And then horizontal means left to right, right to left. Horizontal asymptotes is what we're talking about now. A horizontal asymptote is a horizontal line where the graph approaches, which the graph approaches as x goes to positive or negative infinity. So here, as x approaches negative infinity, the graph of x is approaching the line x equals 0. When x is approaching positive infinity, that line is also approaching 0 on the y-axis, right? To determine where horizontal asymptotes occur, compare the degree of the numerator and the denominator, px and qx, okay? The degree. Remember the degree. I'm just going to go through that right now. The degree is, and I'm going to go ahead and highlight it, what power it's being raised to, right? X to the first, x squared. X to the third, x squared. X to the power of 1, x to the power of 3. X squared, x squared. That is what we mean by the degree, okay? To determine where horizontal asymptotes occur, you compare the degree of the numerator and the denominator. Remember, we're calling the numerator p and the denominator, p of x, and we're calling the denominator q of x. If the degree of p of x is less than the degree of q of x, right? So we have p of x over q of x. You can also just call it n over d, right? If that degree is less than, if the top one is less than the bottom one, the horizontal asymptote is at y equals 0. So another way to write it would be if the numerator degree is less than the denominator degree, the horizontal asymptote is at y equals 0. Okay, and we're not looking at the numbers. We're not looking at 4 and 2. We're looking at the degree only. Okay? If the degree of p of x is exactly the same degree as q of x, you divide the leading coefficients and the horizontal asymptote is at y equals that coefficient. Okay? That is if the degree of the numerator is the same as the degree of the denominator. If that happens, I was trying to make those different colors, but they don't look different enough. The leading coefficients divide the leading coefficients. So I'm just going to label all my leading coefficients too. Here I've labeled my degrees. I'm going to label my leading coefficients. Leading coefficient 2, 4. Set those backwards. 4, 2. 15, 3. Negative 20, 5. Good. Those are my leading coefficients. if the degrees of the top and the bottom are exactly the same. Here we have a 1 over a 3, not equal. Here we have a 3 over a 2, not equal. Here we have a 1 over a 2, not equal. Okay? Here we have a 2 over 2, so that would be equal. So that would be case 2. Okay? In that case, we look at the coefficients. That's the only time you need to look at the coefficients. And also notice that I'm only talking about the leading term. I'm ignoring x squared plus 1. I'm ignoring the constant. I'm ignoring the constant. Okay, we're only looking at the first term. That gives us all the information we need for the horizontal asymptote. Okay, now, if the degree of the numerator is greater than the degree of the denominator, no horizontal asymptote. Okay? If there's no horizontal asymptote, there is a slant asymptote, and then we have to do some long division. Okay? So, on the exams, these graphs will be multiple choice. Okay? Horizontal asymptotes, remember vertical asymptotes, we said that the graph never crosses them. With horizontal asymptotes, they might cross them and come back down, or cross them and go back up, and then go towards them forever. So that can look confusing because the vertical ones never cross. The horizontal ones may cross, but they cross and then they come back and approach. Okay? Horizontal asymptotes are drawn as dashed lines and are not a part of the graph, just like vertical asymptotes. Good? Okay. So remember the rule is, I'll just write it all. If P of X or the numerator is less than Q of X or the denominator, then we say Y equals 0 is the horizontal asymptote. If P of X or the numerator is exactly the same as the degree of the denominator, then we say Y is at the ratio of the leading coefficients. And if the numerator is greater than the denominator, we say there is none. So that's the rule. And you can say P of X, or you can just say numerator. Q of X is always the denominator. Okay, let's look at this. We have f of x equals 12x squared divided by 3x squared plus 1. Excuse me. 12x squared divided by 3x squared plus 1. We're ignoring the plus 1. We just need the leading two terms. And we're going to say, is the degree of p of x, the numerator, less than the degree of q of x, the same as the degree of q of x, or greater than the degree of q of x? And again, we're only looking at the degrees, so we're only looking at the square, the number 2, right? 2 is equal to 2, so y is going to be equal to the leading coefficient. The leading coefficients as a fraction, right? So the leading coefficient is 12 on the top, 3 on the bottom. Make sure you pay attention to any negative signs you might have. 12 divided by 3 is just 4. So we're going to say there is a horizontal asymptote at the number y. Horizontal. Y equals 4. Okay. Here is my graph. Turn that one off. So we're only looking at a horizontal asymptote, so that'll be from left to right, and we see that it is approaching when we go from negative x to positive x. Both sides are approaching this number. If we count, it's 1, 2, 3, 4, right into the 5, and that is the horizontal asymptote we found. Horizontal asymptote at y equals 4, okay? Let's look at this one, even though we didn't solve it. We didn't use the process we just learned, but if we do look at the graph, we can see that there is a horizontal asymptote at y equals 0, right? And y equals 0 is when the degree of the numerator is less than the degree of the denominator. So I'm going to erase that one. Your horizontal asymptote is at y equals 0 when the degree of the numerator is smaller than the degree of the denominator. And we see that that's true, right? Because in the numerator, we have x to the power of 1, and in the denominator, we have x to the power of 2. So that does check out. All right. Number 13, we're just looking at our degrees. So we have 4 to the power of x times x to the power of 1 over 2 x to the power of 2. We're just looking at these guys. 1 and 2. And what are the rules? 1 is, can I get that all in the same picture? 1 is less than 2, 1 is equal to 2, or 1 is greater than 2. Which one is it? It is 1 is less than 2. So we're going to say that the horizontal asymptote is at y equals 0. Oh, and this one's a good example. So I'll show you what it looks like. And what it looks like is the graph crosses y equals 0, but then it's okay that it crosses, right? Sometimes the horizontal asymptotes cross, but then when we look at x as it approaches negative infinity, it's approaching y equals 0. As it approaches positive infinity, it's approaching y equals 0. So that's what it means, and you can check it. Good. 14, again, we're checking just the degree of the numerator versus the degree of the denominator, just the first term. So we have a 3 and we have a 2, right? Is 3 less than 2? Is 3 equal to 2? Or is 3 greater than 2? 3 is greater than 2, so we say no horizontal asymptote because 3 is greater than 2. Here's the graph. So the white one has a horizontal asymptote. It's approaching y equals 0, right? The blue one we said has no horizontal asymptote, and that does look to be true, right? There's no y equals a single number that this line approaches forever as we go from negative to positive infinity on the x-axis. 15, f of x equals negative 20x divided by 5, x cubed plus x squared plus 1. We just ignore all of those, so that just becomes negative 20x over 5x to the third, and then we're just really looking at that 1 and that 3. Is 1 less than 3? Is 1 equal to 3? Or is 1 greater than 3? 1 is less than 3. So we're going to say horizontal asymptote at y equals 0. If you were to graph this, you would see that the line, as we go out that way and out that way, the graph approaches y equals 0. Okay? If you have no horizontal asymptote, remember we said that it is possible that you have a slant or oblique asymptote for that function. Okay? How do you find a oblique asymptote? They only exist if the numerator, the degree of the numerator, so let's keep marking the degree of the numerator is 1 greater than the degree of the denominator. So here we're looking at x, the degree of 2. Here we're looking at a degree of 1. Is 2 1 higher than 1? Yes. Good. So that means it does have an oblique asymptote. And what you want to do is you want to do long division, which I know not very fun, but you only have to do it for a little while. Okay, so if you know that there's a oblique asymptote because the degree of the numerator is 1 bigger than the degree of the denominator, you then take that numerator and you divide it by the denominator. Okay, do you remember how to do this? So you have x squared and you want to turn x into x squared. What do you multiply it by? You multiply it by x, right? X times x just gives me x squared. And then I have to subtract that. My remainder is nothing here, right? And then I bring down the plus 16. Now I have to stop. There's no way for me to divide a 16 by an x, right? So we just stop there. So I say that the oblique asymptote is at y equals x. Okay? The slant or oblique asymptote is replacing the horizontal asymptote, so it's always a y equals. The vertical asymptote is an x equals, but the slant asymptote is a y equals, and the horizontal asymptote is a y equals. Okay? This one, in this case, it's y equals x. When I look at that graph, x squared plus 16 divided by x, I see, oh, and I should include I decided that the oblique asymptote is at y equals x. So I'll put that graph in too, and you can see that as we approach negative infinity on the x-axis and positive infinity on the y-axis, that green line follows, it's very, very close to the purple line. So that's what we're saying with an oblique asymptote. Instead of following a straight horizontal line, it's following a slant. That's what that means, all right? One more oblique asymptote. Again, we need to check, is the degree of the numerator one higher than the degree of the denominator? It is, okay? So we do have an oblique asymptote. It will be at y equals, and then we have to do that long division again. So I'll set it up. Put the top number, top term, top polynomial into the house. Bottom one outside the house. We're going to take x squared minus 6x plus 7 and divide it by x plus 6. So to get x squared out of x, I'm going to multiply x by x. X times x is x squared. 6 times x is positive 6x. And then I need to subtract that. So 6x squared minus x squared gives us nothing. Negative 6x minus positive 6x gives me a negative 12x plus 7. Okay, I'm going to keep going. Here I had to stop because there was no way to divide 16 into x, right? But here, divide negative 12x into x plus 7 into x plus 6. I can do that. And that would be multiply everything by negative 12, okay? If I take negative 12 and multiply it by x, I get negative 12x, and then negative 12 times positive 6. Negative 12 times positive 6. Negative 72. And then I subtract that to get those cancel. And I get, I'm adding those, so that's 79. But it's okay, I can stop, all right? Because there's no way I can divide 79 into a bunch of x's. So that's the equation, y equals x minus 12. Leave off the remainder. Nothing happens with the remainder, okay? So if I were to graph this, and I were to graph the line y equals x minus 12, this graph would approach this graph as it went out, as it got bigger, right? So that is my oblique asymptote at y equals x minus 12. We have one more. All right, for g of x equals x cubed plus 4 divided by x squared minus 25. We do have one higher than the other, right? So we can go straight to division. We've got x squared minus 25. And what we're going to divide by it is x cubed plus 4. Multiply x squared by x to get it to x cubed. X squared times x becomes x cubed. And then negative 25 by x is negative 25x. Oh, sorry, I did not do that right. Did not set that up correctly. Let me redo it. So that was x cubed. I cannot just go straight to plus 4. I need to say plus 0. Oh, I also wrote it too close to the top. Make the house first. All right, x squared minus 25. Here I've got x cubed. I'm not going to go straight to 4. I'm going to say plus 0x squared plus 0x plus 4. So I've got plenty of room for each part of the polynomial. Good. So to get from x cubed to x third, we're going to multiply by x. X squared times x becomes x cubed. Negative 25 times x is negative 25x. But I have to subtract that. X cubed minus x cubed cancels. 0x cubed minus negative 25x is a positive 25x. Put that in the wrong spot too. Okay. Minus 0x cubed minus 25x. Right? So when I multiply negative 25 by x, I don't get any x squared. I think I called that cube too. I don't get any x squareds. Let's make it a big old 0, right? But I do get a negative 25x. So those will cancel. That will be nothing. And then 0x minus a negative 25x gives me plus 25x. And then I bring that 4 down, plus 4. Now, how can I take 25x and divide it by x squared? I cannot, so it ends. So it's just y equals x again. That was dramatic. All my mistakes for it just to be y equals x. All right, and that is how you find any asymptote, the vertical asymptote, the horizontal asymptote, or the oblique asymptote, okay? Now we're going to graph rational functions. To graph rational functions, it looks pretty intimidating, right? But we can either use transformations or you can just use what we know based on this section. We know how to find vertical asymptotes, which is where the function will never cross that x value. We know how to find horizontal asymptotes, which is the graph will approach that line as we are moving towards negative infinity and positive infinity, or the oblique asymptote where it's moving towards negative infinity and positive infinity, but not on a straight horizontal line, on a diagonal, okay? For 20, 21, 22, and 23, we're just going to use transformations of what we know about the graph f of x equals 1 over x. Okay, so we're just going to use transformations at first, right? Use transformations of f of x equals 1 over x for graphing f of x equals 1 over x minus 5. Okay, I'm going to do this in Desmos. I know that that's not, it's easier to see. It'll be a little bit faster, but I know it's not as carefully done as doing it by hand, but it'll be more accurate. Okay, so let's go over to Desmos. And make it a normal size. Hopefully it's normal size. All right, let's start with what they gave us, right? They said the transformation, we're making the transformation of f of x equals 1 over x, and we're just going to use, sorry, we're just going to use the rules of transformation, okay? We're starting with this base, and then they say, what is f of x equals 1 over x minus 5? So what if I subtract 5 from this x? Right now, what happens if we subtract 5? All right, we've got f of x equals 1 over x. We know what that looks like. It has a horizontal asymptote at x equals 0, vertical asymptote at y equals 0, right? Okay. What are the rules of transformation? What is the difference between f of x equals 1 over x, which is what we just looked at, and f of x equals 1 over x minus 5? If we look at the rules for transformations of linear functions, we're either adding or subtracting to the x, adding or subtracting to the y, or making the whole thing negative or making the x negative, right? In this case, we have 1 is the same, the x is the same, and there's now a negative 5 or a minus 5, right? So we're subtracting. Are we subtracting in a horizontal way or are we subtracting in a vertical way, right? Because we didn't make the whole thing negative. We didn't make all the x's negative. We just subtracted a whole number from it. Okay? We subtracted the number 5 from it. Did we do it outside of the x value or within the x value, right? Well, remember that the division bar is a grouping symbol, so that x minus 5 is a horizontal shift. This is a horizontal shift because it's within the parentheses of the x. If it was a vertical shift, it would be outside of the fraction. I'll show you one. Right? That would be a vertical shift because that is not within the parentheses. That's over here. Okay, so this is x minus h, so we're going to horizontally shift right h units. So that means we are shifting right 5 units based on what we know about transformation. We just take the graph of f of x equals 1 over x, we're going to shift it right 5 units. Let's see if that is true by graphing it. 1 divided by x minus 5. Did we shift it right 5 units? Yes, we did. Now, we kind of just talked about this one, but here is f of x equals 1 over x minus 5, all of that plus 3. So it's more like this is one term, and that's another one. Right? Okay, so compared to f of x equals 1 over x, we know that the negative 5 shifts it right 5 units. So that minus 5. And what does that plus 3 mean? The plus 3 is outside of the x, right? So that's going to vertical shift up 3 units. So we just took 1 over x, we shifted it right 5 units because of the negative 5, and we shifted it up 3 units because of the plus 3. Show you. So here's our original. The original's in black, right? We're going to move it to the right 5. Now we're going to move that one up 3. Okay, still the same graph. We just shifted it, translated it to the right and up. Next one, we have f of x equals negative 1 divided by x minus 5 squared. Now, you might be looking at this and thinking, okay, those are very similar. Now I'm just making it negative, right? But look at that squared, okay? Those are not the same because of that squared. So instead of using the base of 1 over x, we need to use the base of 1 over x squared. So let's look at the base of 1 over x squared before we look at number 22. Here is the graph. This is the graph of both of them. So here's 1 over x, right? And then 1 over x squared looks like this because, right, once you're squaring it, you're never going to get a negative number. So that right there got, right, that bottom left, the bottom left of the graph got moved to only positive quadrants. Good. So now we're dealing with 1 over x squared. What is happening to 1 over x squared? Well, we're going to subtract 5. Subtract 5 means shift right 5 units, right? Let's see if that's true. Did we shift it 5 units? We did. So everything got moved to the right 5 units. Now, What else happened? It's a negative. What happens when we have a negative? If the whole thing becomes negative, that would be f of x, right? Now we're going to reflect across the x-axis. So part one was shift it right 5 units. Part two is reflect across the x-axis. Good. So we just flipped it. Here we have f of x equals 1 divided by x minus 4 squared plus 3. Let's see what we can do. We know that this means we're going to shift it right, not 5, but 4. And then what did we learn about the plus 3 over here? Shift up 3 units. We've got our 1 over x squared, shifting it to the right 4 units. And from here, shifting it up 3 units. And what we end up with is the red one. So that would be how you use transformations of parent functions to graph a function. For the last two, we're just going to graph it based on what we've learned about asymptotes and I guess the domain today. Good. All right. So if they say graph the function f of x equals 2x divided by the quantity x plus 5 times x plus 2, what you want to do first is find a vertical asymptote. To find the vertical asymptote, make sure you've factored both the numerator and the denominator. Simplify it if you can, and then set the denominators to 0. So for the vertical asymptote, we've got x plus 5 times x plus 2 equals 0. Take each part. X plus 5 is 0. X plus 2 is 0. X is negative 5. X is negative 2. So my vertical asymptotes are at x equals negative 5 and x equals negative 2, right? Let's see if we can find a horizontal asymptote. How do we find the horizontal asymptote? We have to compare the degree, remember the degree of the numerator and the denominator. Now, this is in factored form. It's not the simplest to see the degree, or maybe it is if you're really experienced. But we know that the degree of this is 1, and here I'm just going to take this out of its factored form, okay? X plus 5 times x plus 2 is going to be x squared plus 5x plus 2x means plus 7x plus 10. All right, so now I can see the powers of the leading terms, right? This is to the power of 1, or the degree of 1. This is to the degree of 2. So my horizontal asymptote is at, where are my notes? In our case, we have a 1 for my px, and we have a 2 for my qx. 1 is less than 2, 1 is equal to, sorry, 1 is less than 2, 1 is equal to 2, 1 is greater than 2. Which one would it be? It would be this one, right? So that means we have a horizontal asymptote at y equals 0, which is nice because then we don't have to find the slant asymptote. And then they ask us to find the y-intercept, because 1 over 2 was numerator less than the denominator rule. The y-intercept could be helpful. So for the y-intercept, you're just going to take all of your x's and make them 0, right? Two times 0 over 0 plus 5 0 plus 2 is 0 over 10, which is just 0. So the y-intercept is at y equals 0. Good. And then for the x-intercept, well, we already found it, right? Well, the y-intercept is at 0. So when x is 0, sorry, when x is 0, y becomes 0. So that's the point, 0, 0. So the y-intercept is at 0, 0, which means the x-intercept is also 0, 0. Or you can just make the numerator equal to 0 if you want to find it in a different example. So what do we know about this graph? Okay, let's really graph this one. Let's take take one coordinate plane and see what we know. What do we know? We know that the graph crosses 0, 0. So this is the graph. The graph is on that point. What else do we know? We know that the vertical asymptotes, there are two of them, one's at -5 and one's at -2. I'm going to take my ruler and I'm going to add those right now. They're not, right? They're not part of the graph. They just help us understand what's happening to the graph. -5 and -2, we're going to get asymptotes. Good. And then we said that our horizontal asymptote is at y equals 0. We have a horizontal asymptote at y equals 0, but it's also crossing at y equals 0. Interesting. Oh, I shouldn't have made it. Imagine it's dashed, okay? Dashed line. That's a dashed green line. What else do we know about it? We don't really know anything else about it. So what do we do with that information? We think about what shapes this graph could possibly be. The graph crosses right here or touches right here, and it has how many parts, right? Let's count them. So it has to be going towards that, towards -infinity. So it's either up here doing that, or it's down here doing this, right? So the first option is either it's here, or it's either here. Here, it has to be either going down like that, or up like that, right? And then here, it's either doing this, or it's doing that, right? So a good thing to do at this point, you kind of imagine it. You say, okay, it's either like this, or it's like that, right? Or it could be up like that, like that. Anyway, there's basically two shapes it could be. Now, if you want to know, basically you want to know whether this is going like this, opening up, or like that, opening down, right? So take x equals -4, figure out what your y is when x is -4. Figure out what your y is when x is -7. Figure out what your y is when x is 1. Okay? So we have 2x is our original function over x squared plus 7x plus 10. And we said we want to know where the graph is up here or down there when x equals -4. I'm going to put in -4 for all those, just because -4 is between -5 and -2. Good? 2 times -4 is -8. -4 squared is 16 minus 28 plus 10, which is divided by 16 minus 28. plus 10. It's 4. So when x is negative 4, y equals 4. So that's a point on the graph. We know that's a point on the graph. The next point we know is negative 4, 4. So it's not going to be down here, right? It has to be going like this. And then I can pick, it's going to be approaching infinity over here. So here, maybe at negative 10. I'll do another one at negative 10. So we're just making an XY table. So we've got 2x over x squared plus 7x plus 10, and it's negative 10. 2 times negative 10 over negative 10 squared plus 7 times negative 10 plus 10 is negative 20 over 100 plus negative 70 plus 10. So that would just be negative 20 over 40. Which is just negative 1/2, right? So when x is equal to negative 10, y is equal to negative 1/2. So that's the point, negative 10, negative 1/2. And you can do as many of these points as you want until you feel like you are ready to graph the function. Good? Maybe we'll do 2. Yeah, we'll just put in 2 just to make sure. So it was 2 times 2 over 2 squared plus 7 times 2 plus 10 becomes 4 over 4 plus 14 plus 10 equals 4 over 28. I guess you could simplify to 1/7. So when x is equal to 2, y is equal to a positive 1/7. Be way down here, but it hasn't crossed that line, right? And let's do one more over here that's past this. So if I know if I'm going up like that or down like that. So negative 1. 2 times negative 1 divided by negative 1 squared plus 7 times negative 1 plus 10. Negative 2 over 1 minus 7 plus 10. Negative 2 over 4 is negative 1/2. Negative 1/2. So when x is negative 1, y is negative 1/2. So that'll be that point. Good. So I think I've got a pretty good idea, right? This is going to go like that. So it's either going down like this or it's going up like this. I could do negative 6 if I wanted to check. So 2 times negative 6 over negative 6 squared plus 7 times negative 6 plus 10 be negative 12 over 36 plus 7 times negative 6 plus 10, 4. So negative 12 over 4 is negative 3, right? So when x is -6, y is -3. And that was a very helpful point. So maybe we should stick them closer to the vertical asymptotes. We know that that comes down to here, right? And we know here it's going to approach 0, approach -5. Here it's going to cross. Approach. I'm really bad at drawing these. Good. All right, last one. We've got f of x equals 4x squared divided by x squared minus 9. Vertical asymptotes. I want you to factor it. So we have 4x squared on the top. X squared minus 9 would be x plus 3, x minus 3. If we set that equal to 0, x minus 3 equals 0, x is 3, x plus 3 equals 0, x is -3. So my vertical asymptotes are at x equals 3 and x equals -3. You can go ahead and add them right now. So again, we're probably dealing with either up, down, down, or down, up, up, if we have a horizontal asymptote. So for our horizontal asymptote, we're going to compare the degree of the two, the numerator and the denominator, right? If the degree is the same, then we take a ratio of the leading coefficients. So it was that P of x is equal to Q of x. So that means it's y equals the ratio 4/1 or y equals 4. Okay, so the horizontal asymptote is at y equals 4 way up here. And I'll remember to make it a dashed line this time. Good. And then we're just going to make a table of x and y. What would I use if I only had 1, 2, 3, 4 to do, right? I would use -4. I would use 0 because it's easy. I would use +4. And I would see if that gave me enough information. Okay, so let's solve each of those. We have 4x squared over x squared minus 9 when x is -4. So that becomes 4 times -4 squared over -4 squared minus 9. -4 squared is 16. 16 times 4, 64. And then here we have 16 minus 9 would be 7. And that's okay if it's a fraction. It's just close to the number 9, okay? So when x is -4, y is 9.14. So when x is -4, y is way up here, 9.14. Good? All right, what about when x is 0? So we've got 4, 0 squared over 0 squared minus 9. So that would be 0 over -9, which is just 0. So when x is 0, y is 0. So it's going to go through that point. And then over here, I set up +4. So that's 4 times 4, sorry, squared over 4 squared minus 9. What did we say 4 times 4 times 4 is? 64. And then 16 minus 9 is also 7. So 64 sevenths. So it's the same as over here. They're kind of identical. So what I would do with that information is I would make this approaching +3, this approaching 4. Make that look like that. This approaching -3 and approaching 4. That's how I would graph it. All right, guys, thanks so much. And please email me if you have any questions. Have a great day.